Good morning, students. Today we are going to discuss regarding the next topic, that is translation, lattice translational vector. In the last class, we discussed regarding the introduction of what solid state physics. What is solid state physics? It is a branch of physics. It is a study of what macroscopic material, study of macroscopic properties of material or solids by knowing the microscopic properties of, or by knowing the microscopic arrangement of atoms, molecules or ions. That is the study of solid state physics. Okay, what is solid state physics? It is a study of macroscopic matter or macroscopic properties of matter by knowing the microscopic arrangement of atoms, molecules or ions. Next, we also discussed what is lattice point or what is lattice, space lattice. Lattice is nothing but what? They are regular arrangement of points in a space. Regular arrangement of points in a space, nothing but what? Lattice points, okay, or lattice simply, okay. Each and every point in the space or space lattice will be having the same environment when we compare with the other point in the space. Okay, so that is called lattice points or lattice space. We can call space lattice simply, right? And we also discussed regarding the we also discussed regarding what in general here. Now next we have lattice translational vector. Lattice translational vector. What is lattice translational vector? Already in the last class we discussed. Okay, let us consider in a space some two-dimensional. We are taking two-dimensional lattice points in a space. So this is what two-dimensional lattice points in a space. We took two-dimensional space lattice. X and y axis in a space, okay, two-dimensional space lattice. Now let us consider one point A, okay, let us consider point A, it has an origin. Let us consider point A is an origin. Now if you take the distance between the nearest point, let us consider A, B, C, D. These are the non-collinear, nothing but lying, does not lying on the same plane. Okay, same line. Non-collinear points, A, B, C, D are non-collinear points. Let us represent the distance between A and B is A bar, and B and A and B is B bar. Now, A bar and B bar represents what? Primitives. Okay, primitives are the smallest distance between the 2 points or the nearest points. Nearest point, the distance between the two nearest points. Okay, this A bar and B bar are called lattice translational vectors. Okay. Now, in general, the position vector, in general, the position vector of the lattice is represented by R bar equal to N1 A bar plus N2 B bar for this particular two-dimensional lattice. Okay, the position vector R. See, this is origin. Okay, this is origin A. Now, if the distance between, for example, any 2 points, let us consider this is the 1 point with respect to the origin. Now this is what? Position vector R. This position vector R is represented by what? N1 A bar plus N2 B bar. Simply addition of A bar and B bar. This position vector is represented by addition of A bar and B bar, where N1 and N2 are what? Integers. integers. Okay, some value, they may have some value. Okay, it is for two dimensional, the position vector. See, simple. You know that simple. This is A, this is B. The resultant position vector R is nothing but what? A plus B. N1 into A plus N2 into B. Simple. Where A is the origin. Okay. So like that, where A and B or A bar and B bar are nothing but what? Lattice translational vectors. They are also vectors. Simply it is addition of two vectors. It is only the direction showing the point from one lattice point to the other point. It is showing the way from point A to point B. Simply from point A to point B, A B bar is equal to A bar in the lattice. These are the imaginary points, concepts. Okay, now like that, A B bar is B bar. Now A C bar is what? Our R bar, which is equal to how much? N1 A plus N2 B we are calling. Where N1 and N2 are some integer values. The distance between these 2 points. Okay? N1 and like integers. So, like this, we represent a two-dimensional, what we can say, lattice. Position vector of the two-dimensional lattice. If we take three-dimensional, it will be N1 A bar plus N2 B bar plus N3 C bar. We take three-dimensional lattice space. Okay? So, like this we represent the lattice translational vectors. Simple. Okay? We are taking the whatever the entire lattice in 2 dimension or 3 dimension. Okay? The nearest distance, if you take any origin, if you take any point as an origin, right? The distance between the 2 points, the nearest points, are represented by some vector. Those vectors are nothing but what? Translational vectors. Okay? So, and again, we have some operations also. Okay? They are not needed. Okay? We will see in the further classes. Okay? This is the representation of position vector of lattice translational vectors. Okay? Now, next we have unit cell. See, in the last class, we discussed regarding the what is lattice and what is basis. Lattice plus basis will use what? Simple, complete crystal structure, isn't it? So, we know that. See, if you take some lattice points, okay, if you take some lattice points in space, these are imaginary points. Now, replace each and every point with some atom. Okay, with some atom. What you get? All are atoms. For example, carbon atoms. We get carbon solid, simple. Carbon atoms are completely placed, arranged one after another in the space. Now, the entire thing will use what? Carbon crystal. Isn't it? Carbon solid. Right? So simple. Right? So like this, see, lattice nothing but what? They are imaginary points. Base is nothing but what? Atoms. Maybe atoms there, they are maybe molecules. Okay? So, if you place continuously the same molecules, if you arrange the same molecules, what will get? If you arrange the same calcium carbonate atoms, what will get? A solid, a crystal, a solid, a chalk. Okay? Similarly, here also, lattice plus basis will use crystal structure. Okay? So, now, what is unit cell? Let us discuss regarding unit cell. Unit cell. Unit cell. See, for example, if I take a wall, okay, a wall is made up of what? Some bricks, isn't it? Like this, a wall is made up of what? Some bricks. Similarly, if you take a crystal, okay, the smallest solid, the smallest element the repetition of which will gives the complete crystal is nothing but what? Unit cell. See, if you take a wall, okay, wall consists of what? Same size bricks. If you place one brick after the other like that throughout the three-dimensional array or through the two-dimensional array, what we will get? We will get some volume. We will get some wall or a volume. Okay. Now, see, the smallest unit, nothing but what? We are repeating the same brick through two-dimensional or three-dimensional. We are getting a wall, isn't it? So this is the smallest unit. By replacing one after another the same brick, we will get a wall. Similarly, if you place the same unit cell, one after the other, throughout the three-dimensional space, you will get a complete crystal. Nothing but what? Simply, the unit cell is nothing but what? A smallest geometrical figure, the repetition of which throughout the three-dimensional space will give a complete crystal structure. Nothing but what? Unit cell. Unit cell is the smallest unit of the crystal, the repetition of which throughout the two-dimensional or three-dimensional you get a crystal, complete crystal. Simple. See, let us consider a small element of a crystal. If we repeat this small element again and again, okay, again and again, okay, we will get what? A complete crystal. This small unit is nothing but what? Unit cell. Okay, right? Did you understand? So, what is unit cell? A smallest geometrical solid or figure, the repetition of which will give the actual complete crystal is nothing but what? Unit cell. In the next class, we will discuss Miller relation. Okay, thank you, Anand.